series of discussion on the chemical thermodynamics. Today, before going to the formulation, mathematical formulation of the first law of thermodynamics, let me explain three energy terms. And these three energy terms are totally involved in the mathematical formulation of this first law of thermodynamics. These energy terms, first one is the work done, and second is the heat transfer, and third is the internal energy. Among these three energy terms, this work done and heat transfer is being exchanged between the system and surrounding. But this internal energy is totally the property of this system. So first I like to define the work done. And it is given the symbol W. Whenever a body moves, when this surrounding exerts a force on this body, and this body moves through a distance, suppose dx, and here it is the directions of the sets, and from this to this, the displacement dx and the surrounding gives an energy, gives an force which is equal to Fx. Fx is the force along the direction of this displacement. So the work done on the system, this one equal to Fx into dx, where Fx is the force exerted by the surroundings along this x direction. And dx is the displacement of the body or the matter along x direction. So this is the definition of this work done in all respects. And the sign of W is that when Fx and x are in the same direction, this W becomes a positive. It means what is done on the system by the surrounding. By the surroundings means energy flows from the surroundings to this system or this to work and this body, and energy of the system is increased. And when this one is a negative, and when Fx and x are in opposite direction, are in opposite direction, W is equal to negative. Means so what? Done by the system. By the system on the surroundings. On the surroundings. Surroundings. That means in this case, the energy flows in the form of work from the system to the surrounding, and energy of the system is decreased. We may consider this work done W may be of different types depending on the nature of this force Fx. And first of all, I try to discuss the mechanical work or the pressure volume work, which is very common in thermodynamics. So first we shall define a mechanical work. Or pressure volume work. Pressure volume work. Now, let us consider one cylinder which contains a certain amount of this gas, and let us first discuss the compression of the gas. And here it is the internal pressure which is within this gas, and here this external pressure means the pressure exerted by this surrounding. And directions of this external pressure is this way. And when this P external is greater than P internal, this piston moves in this direction. Means X is moving in this direction, and this piston will continue to move in the downward directions, and becomes, when external pressure becomes equal to internal pressure, the piston stops. Suppose piston stops here, and whenever these two are the same, this system attains mechanical equilibrium. And this suppose this is the dx displacement of this. This is the displacement of this piston, and if area of this piston, area of cross section of the piston, then W equal to Fx into dx. And this Fx we can write this P external into this area. Pressure into area will give you the force. And here it is the displacement dx. So we can write a P external into A into dx. And A the area of cross section, dx is the displacement, and both the multiplication of the two will give you the volume change that occurs by the applications of this external pressure. Means it is the pressure given by the surroundings. And this one will give the P external into volume change. dV is the volume change. So this work, in this case, this work is external pressure, which is the force per unit area, and the displacement x, both are in the same direction, and so this sign of this W is the positive. Means work done on the system by this surroundings. And if this is the surrounding, then in this case the energy flows in the form of work from the surrounding to the system, and the system is having the higher energy, and the system energy of the system is increased by this process. And another and in the compression of this work, W is a positive. If we consider the work of expansion here in a similar fashion, this is the piston having the area cross section A, and it is the external pressure, the external pressure. There a definite amount of gas is confined within this system. Here piston in thermodynamics is an idealized piston, which piston is weightless, frictionless, unmovable up and down. So in this case, suppose P internal, P IN is the internal pressure of this gas, and this is the external pressure. External pressure is there. And you know, whenever the external pressure and internal pressure becomes the same, this piston remains static at this position. Means these two, system and surrounding, are in equilibrium, mechanical equilibrium. If this internal pressure is greater than external pressure, it is to be remembered that external pressure we can only change by applying this weight on this piston. It is not the internal pressure that we can change. So in this case, internal pressure is greater, so piston will move in this direction. Displacement will be there. So in this case, the direction of this external pressure and the displacement are in opposite directions, and there occurs an expansion of the gas. Since these two are the different directions, so W is equal to negative. Means work done by the system. And in this case, suppose this is the surrounding. So here this energy will move in the form of work from this system to surrounding, and energy of this system will decrease. And you know, this increase of this piston will continue. Expansion will continue so long until the P internal is equal to this P external, and the system attains this mechanical equilibrium. So this is all about the mechanical work, and in the expansion and compression, it is the compression, this is the expansion. In the compression, energy is added from the surrounding to this system, and in this expansion, work done by the system, and energy will flow from system to the surroundings. So this in a short way, if we define define W. W is the work done according to the IUPAC convention. Work done on the system by the surrounding, and this one equal to minus V external into dV. Or we can write for a finite change P external into V2 minus V1. This is the volume change. So for compression, V1 is greater than V2. So this term is negative, and pressure, external pressure is always positive, and minus, and here minus. So this work is positive. Means work done on the system by the surroundings. For expansion, this V2 is greater than V1. So this one is positive, this is positive, preceded by negative sign. So what is negative? Means work done by the system to the surroundings. Whenever the process is reversible, means infinite change, by infinite small way, this external pressure is increased or decreased. In this case, it will proceed in multi-step process, and every step the system attains equilibrium. In that case, the external pressure and internal pressure both are the same and can be written as a P. So in that case, work equal to minus P dV. P actually the external pressure, but in a reversal process it is always at every step equilibrium remains equilibrium to this internal pressure. So external pressure, internal pressure are the same. Now I like to explain another form of work, which is also sometimes used. Depending on the type of the force, if Fx is the gravitational force, then suppose this is H equal to 0, ground level, and here some body is there and it is moving to this height H, means X is increasing, and here this body rests there, and this body is of mass M, and by external force, means Fx external force, this is lifted from this height to this height. So it is the gravitational work, means this work is done by this body against this gravitational work. In this case, the displacement and the applied force both are in the same direction, and so this W, gravitational work, equal to this Fx into dx, and it is equal to Fx equal to the mg. Mg means the force by which the Fx is being lifted, and it is this h, and so it is equal to mgh, and whenever it is lifted, this W is a positive. Means work done by the surroundings to this body, and this body will acquire this energy in this work in the form of energy, and it is the potential energy. This potential energy of this body is equal to the amount of work required to lift the body of mass M from this level to this level. Whenever it falls, loading down, then in this case, work is negative. Means the system is doing one. So in the same fashion, we can explain the electrical work, magnetic work, and work due to the surface tension. These are all forms of work will be there depending on the nature of these effects. Now I like to discuss the another term, the heat transfer. Heat transfer is also very important in thermodynamics. And here the heat transfer, and this transfer occurs from the system to surrounding or surrounding to system. Heat transfer is Q. Q, this heat is also a form of energy, and heat is also a form of energy. And whenever this heat flows, say heat according to our common sense, we know the heat flows from a body at high temperature to a body at lower temperature until the two body has a common temperature or equal temperature. In that case, this system to the two bodies attain the thermal equilibrium. So this heat is a different, is to some extent a different form of energy or unique form of energy. As you know, every form of energy could easily be converted into heat energy. As you see, if I rub these two hands, then I am doing this mechanical work. This mechanical energy is being converted into heat energy, and this the two hands is being warmed up. Or suppose you are taking a bath in a pond in early morning in winter season. Your body is trembling, means all the muscles of your body is vibrating, means that your body temperature is decreased. So this body automatically doing some mechanical work by vibrating its muscles to convert this mechanical energy into the heat energy, and this heat energy will increase this temperature of this body to 98.4 degree Fahrenheit. So it is seen that the heat is easily converted, other forms of energy are easily converted into heat energy. Suppose some electricity flowing through a conductor, electrical conductor, automatically the electric conductor is being heated up. But the heat has no such tendency. But heat has no such tendency to be converted into other forms of energy. It is a very peculiar. If we like to convert this heat energy into mechanical energy, it is not so possible. We require an engine, and engine will convert this heat into mechanical work, and I shall discuss in second law of thermodynamics. There will be a fraction of heat will be converted into mechanical energy by this engine. So engine will do this work, and scientists are taking so much attempt to convert this heat into mechanical work, as the universe contains a vast store of heat energy. So this and how this heat energy will be utilized. This is the task or the challenge of the scientist, and how the efficiency of this conversion of heat into energy, heat into mechanical work would be increased. And this regarding the sign of Q, when Q is positive, means the surrounding is supplying this heat to the system. It is the system, suppose. It is the system and it is the surrounding. So in this case, Q, whenever Q is supplied from the surrounding to the system, Q is positive and heat energy and system will gain energy. And when Q is a negative, means the system Q is negative, then in this case the system is giving up the energy, heat energy and the system will lose energy. So far I have discussed this heat work done at heat energy. These two are the forms of energy that are exchanged between the system to surrounding or surrounding to the system. And this third one, this C, it is the internal energy. And it is denoted by U. Internal energy is a specific property, a certain property or definite property of the system itself. And the internal total energy, suppose the total energy of a body or the matter in the system is equal to the T V plus E, and it is the total energy and it is the kinetic energy when the body or the system as a whole moves from one place to another place, macroscopic movement, and it will produce this kinetic energy, and it is the potential energy. If the body is in some external force, external field force, as we have seen, whenever the body is lifted against this gravitational force, gravitational field force, and in this case this body acquired this potential energy equal to mgh, and this one is the internal energy. So whenever the system is raised, whenever the system or the body is at rest, then kinetic energy equal to 0. This potential energy is also equal to 0. No external force field is applied to this system, and in this case the total energy and becomes equal to this internal energy or equal to Q. So now the question is coming, what is the origin of this internal energy? Now let me discuss the internal energy. Origin of internal energy. It is actually coming due to the constituent particles like molecules in the systems, and the origin comes up between the two types. One is the molecular motion. If these particles are the molecules, then it is the molecular motion of the molecular motion within the system, and this will contribute this internal energy. And this molecular motion, maybe it is a translational motion. It may be the translational motion, translational motion means a molecule. Molecule goes here and comes here and comes in this way, and this is the transfer. But it is the motion of this molecule when the molecule is moving from one point to another point in space, and it is the translational kinetic energy. And another is the vibrational motion. In this case, suppose in this case I may consider this is one atom and this is another atom, and this is the center of gravity, and these molecules are compressed. The atoms within the molecules are being compressed and elongated, and this elongation and compression will go continuously, passing through this equilibrium bond distance. And other is the rotational, another is the rotational motions. Means here is the atom, here is another atom, this is the center of gravity, and this molecule is rotating. And this rotation of this molecule gives this kinetic energy, and these molecular motions that constitute this internal energy. Not only that, the motion of electrons and the nuclei within the molecule will also constitute the internal energy of the system. All these are called internal kinetic energy. And another is that another sort of internal energy is coming due to molecular interaction. Molecular interactions. The two molecules, there is a molecular attractions or molecular repulsions. Here is one molecule, here is one molecule, and these molecules are being either attracted or repulsed according to the Van der Waals forces. Not only that, here is the suppose nucleus, here is the electron. So this force, there will be attractive force, and this is another electron. This is attractive force, and this force will give this attraction potential, and this one is the repulsive potential. So these are also constitute the molecular internal energy, and this one is called the internal potential energy. So whatever, these are the origins of this internal energy. But whenever the substance is placed in some external field force, this will not be the internal energy, this will be the external energy. It is quite obvious that thermodynamics does not consider the constituent of the systems. Molecules or colloid particles or atoms, the thermodynamics does not bother. So naturally, by means of thermodynamics, we cannot measure this internal energy. Internal energy, of course, maybe quantum mechanics or statistical mechanics, they can help to find out this absolute value of internal energy of a system. And every substance has some energy stored within itself. It is obvious. Suppose say 1 mole water, liquid water, at 0 degree centigrade and 1 atmosphere is converted into 1 mole ice. 1 mole is solid and at the same temperature and same pressure. But whenever this state is going to from this state to this state, this system is going on. This will liberate this energy 18 into 80 calorie per mole. So if this water does not have any energy stored up, then why this amount of energy is being released? Not only that, in a Daniell cell, you may consider the zinc plus copper sulfate and gives you the zinc sulfate plus copper. Whenever this reaction is done in a beaker, enough heat energy is being evolved. But if these two substances are not having energy stored up, then how the heat energy is being released? Not only that, if the same reactions it will do in a Daniell cell, then Daniell cell will produce this electrical energy and naturally. And whenever suppose another thing very simple, suppose we are burning this carbon. If we burn a carbon, then vast amount of heat energy is released. Suppose this is a book, this is a copy, and if we burn this copy, then vast amount of heat energy will be released. If this one is not having any energy stored up, then how this energy we can get it? So all these things show that every substance, due to its existence, always some energy is being stored within itself, and this energy is called internal energy. And this internal energy is a state function, and this internal energy is extensive in nature. Extensive in nature means if we take this double amount of the substance, double amount of this material in the system, then internal energy will, then the number of molecules will also be double, and this internal energy will also be double. Means it depends on the amount of this material present in this system. Not only that, it is this U is state function and single value. We may draw one picture. Suppose U is a function of a temperature and volume. So we can draw a diagram. This is the temperature and this is the volume, and this is the point. This is the starting point, initial point, or the initial state of this system defined by T1 and V1, and it is the U1. One subscript is given for this initial state, and two subscript is given for this final state. It will continue. This convention will continue throughout the whole thermodynamical chapter. And suppose this system moves to this state, and this is A, suppose, and this is B, and here the internal energy U2, and this is, and the U2, and the position of this final state of this internal energy is given T2 and V2, and whenever the system changes its state, the internal energy also changes. This internal energy is equal to U2 minus U1. And naturally, if we change this path, say suppose if we go in this path 1, or if we go in this path 2, the delta E will be the same for the given two states of this system. So it is a state function. So first criteria, it is a state function. Second criteria, delta U. Delta U is fixed or constant for a given states. Two given states of the system. Not only that, if we come if we go to by path 1 and coming to this path 2 and coming to this initial state, then this process is a cyclic process, and in this case cyclic process, integration and the U and equal to 0. So since they are coming to the same state, and same state means the same internal energy, and so energy change. And this is third one. And this is fourth. Since U, let us take this U is a function of temperature and volume. So it follows the Euler's relations. Euler's relation means del 2U divided by del P del V equal to del 2U divided by del V del P. This relation will hold if this for the case of U, since U is the state function, perfectly differential, and it is also strictly linear. And it is to be remembered that this Q1, and if it is the Q2, then Q1 is not equal to Q2. For this path, Q1 will be different than Q2, as Q is a path function. Similarly, this what also similar case 1, W1 and W2, and this for these two states, this Q1 not same and W is also not same. And whenever it is coming to this cyclic process, then del Q, or as it is not perfectly differential, so this is not equal to 0, or the cross W is also not equal to 0. In my further discussion, I will explain all this phenomena again. So this is all about this work done, heat transfer and internal energy, and I think these discussions will help not only for the IIT-JEE aspirants, but also NEET and other state examinations. In every case, this form of discussions will help. And thanks to you all who are watching this video.